Hello and welcome to Numeristical. This is part 2 of our series on classification, a discrete probabilistic point of view. If you haven't looked at part 1 first, you might want to go back and watch that first. But to revisit, give some context, so we were talking about our classification framework where we have predictors represented by X and a target value represented by Y. And we're working in this paradigm where we say we're going to get some training data. From that training data, we're going to build a model, and then we're going to use that model to make predictions. And we wanted to define what we mean by each of those things. So part 1, we talked about what is a prediction. And now we're on part 2, where we're going to talk about what is training data and talk about some representation and some notation about it. So what is training data? Well, again, we've got the predictors represented by X, the target or the outcome is represented by Y. And typically X is multivariate. We have numerous features that we want to use to try to predict Y. And we're going to use the letter R to represent the number of features that we have. So for example, if we have a problem where we want to make predictions about individuals, and we have their age and their height and what state they live in, then X1 would be the age, X2 would be the height, and X3 would be the state. And we would have 3 features. And collectively, those 3 features would be our X. Now, Y is typically simpler. It's just one column. And we're going to use 0 or 1 if it's a binary classification problem. And typically, we'll use the integers 1 through k if it's multi-class classification. In some cases, we might use 0 up to k minus 1. And the key point is that the training data are assumed to be a set of independent observations from a probability distribution P of X and Y. So the way to think about this is there's some probabilistic dice rolling universe that's generating this data. And we want to understand what's behind these sort of dice rolls. And we have training data. We have observations from this, and we're trying to kind of reverse engineer, given the data that I've seen, what do I think is the mechanism that generated them? And so there's 3 ways to represent training data that we're going to talk about in this video. The first is called the data frame. This will probably be the most familiar one to people. That's where we have a table of our feature values and our target values. The second is what I'll call a data list, just a list of XY pairs. And the third is called the count matrix. This might be the less common one that fewer people have seen or thought about. And that's where we're going to actually count how many times each XY pair occurred. But in order to define particularly the third one, we have to make this discrete assumption. The title of this series is that it's a discrete probabilistic point of view. And we talked about in the last lecture why it's probabilistic. Here we're going to talk about why it's discrete. And what I mean by discrete is that we're going to assume that X has finitely many possible values. Now this may seem a little strange or unusual, but we're going to see it's actually pretty straightforward and easy to do. Anything that's an integer, if we set a max and min value of it, we now have a finite range of values for that integer. Anything that's numerical, we can set a max and a min and also a minimum increment, and that will make a finite number of possible values. And anything that's categorical, we just need to enumerate all the possible values. Now, one thing to keep in mind is that computers have finite memory. So anytime you're putting data on a computer, there's, for any different variable that you have, there are a fixed number of bits that are being used to represent that data. And so whether you realize it or not, there are actually, in any data set you're working with, finitely many possible values for each of your variables. Now, it might be very, very big, but it's always going to be finite. One thing I want to mention is that this is a conceptual framework, so we're not going to actually have to set these maxes and mins explicitly or these increments explicitly. This is a way to understand some of the mathematical properties behind supervised learning. And in particular, to define this count matrix that we're going to get to at the end, it's going to be very useful to assume that X has finitely many possible values. Okay, so let's go into the first representation, which is the data frame representation. And this is the one that people are probably the most familiar with. So again, if I have my 3 features, age, height, and state, and my target is broccoli, so whether someone likes broccoli or not, then we would see it represented in a tabular form here. And if you work with Python and pandas or R, you should be quite familiar with the data frame object. If you work in Excel, as an Excel spreadsheet, the data frame is essentially the Excel spreadsheet representation. Each row is a data point, and we have columns for the different values of the feature and 1 column for the outcome. Now, since I've got a finite number of predictor values, let's think about how that would look. So age is between 20 and 100. That means there's 81 possible values. Height, let's say height is in meters, and we're going to say people are between 1 and 3 meters tall, and we only care about increments of 0.01 meters. That would give us 201 possible values. For US state, we're going to think about the 50 US states plus DC, so there's only 51 possible values. So that would mean that X has 830,331 possible values. So we could list them all. We could just write a list of every single possible value of X. And once we list them all, that means for each unique combination, we can assign a unique integer between 1 and 830,331. Now again, we don't need to do this explicitly, but we're going to kind of walk through this exercise again, just as a conceptual framework to understand a few things. So when we list the possible values, here's how we list them all. We start with the smallest age, the smallest height. We go through the 51 states. Increment height by its smallest increment. Again, go through the 51 states. Keep going until we've reached the biggest possible height. And then we increment age and start all over again. And if you go through this, you'll see that here would be the unique integers we would assign to each of these combinations. Next, I want to talk about the data list. So how would we go from the data frame that we just showed before to a list where it's just a list of XY values? Well, it's fairly straightforward. The first thing we're going to do is take our predictors X and think of them as a triplet of feature values. So in this case, age, height, and state together, that triplet is going to be considered one thing. And so we have XY pairs this way. And then using the mapping that we came up with before, we can assign each triplet of values to a unique integer. And then our XY pairs just look like pairs of integers. And we would think of our training data as being a list of pairs of integers. Next, we're going to talk about what I'm going to call the count matrix. And this is where it's going to be important that we said that X has finitely many values. So we're going to let M be the number of possible values of X, K is the number of possible values of Y, and N is the number of training data points we have, how many data points we have in that data list. So our count matrix then is going to be an M by K matrix, M rows, K columns, and an entry in that matrix, so the entry in the ith row and the jth column, is going to correspond to how many times we've seen the exact training data point where X equals I and Y equals J. So remember, in our data list, we had a list of pairs, and each pair had an X value and a Y value. The X value was an integer between 1 and M. The Y value was an integer between 1 and K. And so every time we see a point in that data list, we're going to increment the counter in the count matrix that corresponds to it. So if this is my data list, so imagine I just had kind of these 4 data points in my list, my count matrix would look like this. So for each of my data points here, I filled in a 1 for the corresponding entry in the count matrix. And everything else we don't see. If these were our only 4 data points, everything else in this matrix would be 0. So to make this a little bit more clear, I'm going to switch over to a Jupyter Notebook now, where we can play around and actually go through what this would look like with some simulated data. Okay, so we're in the Jupyter Notebook now. This notebook is available at this web address. I'll also put that down in the comments so you guys can click and follow along. And what we're going to do here is first I'm going to list out all the US states. There's 51 values, including DC. Put that in a NumPy array. I'm going to make a dictionary where I map each of those values to an integer between 0 and 50 inclusive. Next, we're going to generate some data. To start out, I'm just going to generate 1,000 data points. And I'm going to generate age as an integer between 20 and 100, just as we discussed before. For height, I'm going to make it a little bit smaller in range. So I'm going to let the height in meters go between 1.0 and 2.4 and just have an increment of 0.1. And in this way, we'll have 15 possible values for height. And for state of residence, again, we have those 50 values in DC. And we're going to generate random values for binary target. We're going to say that 40% of people like broccoli, no matter independent of your age, height, or state, just to make it simple, since we're just talking about how to represent the training data. So now we can just take a look at what these things look like. So if you look at x1, our age, you see they're integers between 20 and 100. If we look at the height, again, they're numbers between 1 and 2.4 with increments of 0.1. If we look at the states, we'll see different values of states. And if we look at our y, we have zeros and ones. Now I'm going to put these in a pandas data frame to illustrate the data frame object. And so you'll see, this is our data frame representation, age, height, and state, and broccoli. And we have 4 columns. Should be pretty straightforward to anyone who's worked with this. Next, we're going to map each of these triplets to an integer. So the next code is just doing some kind of clever accounting and bookkeeping to map each unique combination of age, height, and state into a different integer. So we're going to take the age, make sure the age goes from 0 to 81, make sure the height goes from 0 to 14 for the 15 possible values there, and that the state goes from 0 to 50. And if you look at the different values represented, you'll see that we're missing some values because our data set is small, but age goes from 0 to 80, height goes from 0 to 14, and the state goes from 0 to 50. And so since we have 81 values of height, of age, 15 of height, and 51 of state, there's 61,965 different possible values of x. And we're going to map each column to its corresponding integer using this clever math. And now, from this, here's our data frame, and here's the corresponding data list. So this person whose age was 31, their height was 22, and their state was Massachusetts, corresponds to the integer 9046, and so forth for everybody else. If we don't want to represent the data list in this manner as a table, we could also just represent it as a list of tuples, and we do that this way. So again, it's the same information, just in a different Python object here. Now, here's the fun part. We're going to generate this count matrix. So how do we generate this count matrix? I've got this list, right? I am only showing the first 10 data points. But if I've got this list and I want to convert it to the count matrix, it's pretty simple. First, I just initialize a matrix of zeros that's going to have this many rows, 61,965, and 2 columns. So I'm going to make this matrix, initialize it to 0. Then I'm going to iterate through every point in this data list, and every time I see a pair xy, I'm going to increment that part of the matrix by 1, that entry in the matrix by 1. So if I look at the count matrix, it doesn't print out the whole thing, and the values that we're seeing here are all 0. So let's look for a place where there should be a 1, so like 3876. So let's look at the count matrix of 3870 to 3880. And here we see, here's the entry that has a 1. So in this case, the count matrix is very, very sparse. And the reason why it's sparse is we only have 1,000 data points, but there are 61,965 times 2 possible entries. So we've only made a very, very, very tiny fraction of these entries could possibly have turned to 1. So let's go back and see what happens. What if I change my number of data points to 1,000,000 and regenerate this count matrix? So we're going to do that now. I'm going to make this 1,000,000, and I'm going to reiterate through all of these cells. And now we see that the count matrix typically has a lot more values in it. Almost all the cells are populated, and they all have, reasonable numbers inside of them. And the last thing I want to show here is that if we take this count matrix, I'm going to do a normalization on this count matrix where I take each row and I'm going to divide it by the sum of the counts in that row. So for example, this row that's 7 and 3, the count is 10, so I want to convert that into a row that says 0.7, 0.3. And this is the Python code to do it. I generate the row sums, and I do this little tricky transpose arithmetic. And now you'll see, so for example, this row, which had 4 zeros and 2 ones, is now represented by 0.6667 and 0.3333, and so forth. And the reason why I bring this up is to show you that this count matrix, again, what would we expect as this count matrix got really, really big, as the number of data points I put into this count matrix gets really big? As it gets really, really big, these entries should get close to 0.6.4. This one happened to hit it exactly. That was kind of luck for such a small number of data points. But as we put more and more data to it, since the right answer in this case is that everyone should have 0.4 probability of liking broccoli, being a 1, and 0.6 probability of not liking broccoli, as we get enough data, all of these entries should converge to 0.1. So actually, let's go back, and I'm going to make this a little bigger. I'm going to make this, let's see what happens if I make this 10 million and go through all of these cells. Okay, and as we see now, finally, so we finally finished. It took about 5 minutes or so to run on my machine. Might take even longer on your machine. But we go through the whole thing now with 10 million data points. And what we see is now in every row, we're pretty darn close to 0.6, 0.4. So that's interesting. And the reason why I wanted to demonstrate that is to show that this count matrix, as the counts get big, if you do that normalization by rows, starts converging to the true conditional probability matrix. And we'll talk about that more in the next couple of lectures. So to start wrapping up what we've shown so far, let's summarize the different training data representations that we talked about today. One is the data frame, where we've got one row per data point, and we list the feature values of X and the corresponding value of Y. This is your Excel spreadsheet view, or your Pandas data frame, or your R data frame, how typically that would represent the data. The second is this data list, where we now think of a list of XY pairs. And in this case, we think about X and Y as just being integers. We use this idea that there's a finite number of possibilities of X and a finite number of possibilities of Y. And so our data list is just a set of pairs of integers. And then third, we have this count matrix, where we actually said, I'm going to make a matrix of all the possibilities of XY, since there's only finitely many of them. And I'm going to let the corresponding entry in the matrix tell me the count, how many times I've seen each particular value. And one perspective that I want to give is that the efficiency of these representations really depends on the relative sizes of n and m times k. So when n is much smaller than m times k, so what does that mean? That means the number of things we've seen, our data, our training data, is a small fraction of the number of possibilities of things we could potentially have seen. That's what this m times k represents. In that case, the count matrix is very sparse, and therefore it's a really inefficient representation. It doesn't make sense for me to list out or have an entry for everything I could have seen when most of the things I've never seen, and I only have ones for a relatively small number of values. That's an inefficient representation. So that's why you don't see it used that frequently. In this case, it makes a lot more sense to represent your data by just listing the things that you've seen and assuming everything else was not seen. Conversely, when you have a lot of data relative to the number of possibilities, so n is much, much bigger than mk, that's another situation. And in that situation, the count matrix is actually a more efficient representation because the number of data points is a lot more than the number of possibilities. Data was inevitably repeated, so it's actually easier to store the counts than to list data points multiple times. And that's what we saw in the Jupyter Notebook when we let the number of data points go to 10 million or 100 million, and there were only 125,000 or so possibilities. What we saw was that actually the count matrix is a more efficient representation. And interestingly, the final point being that count matrix actually starts converging after we normalize by the row sums to the true probability matrix. And that's something we're going to talk about in the next lecture. Okay, well, thanks for watching this video. If you're interested, please continue to part 3. If you could like or subscribe to this video, that would be great, would help me out a lot. Please leave a comment below. If you have any questions or just want to show that you're watching, that would be great. And also, if you'd like to make an account at www.numeristical.com, this way when I do live events, you'll be added to the Slack channel so that you can participate in those. Thanks very much, and have a great day.